Hello everyone, welcome back to another episode in the Logistic Regression series. Logistic Regression, and here we'll be looking at more math and intuition behind logistic regression. And we're gearing up to implement it from scratch in Python. And if you're following along, please don't forget to subscribe and hit the bell icon so that you get notified whenever I do post a new video. And I also want your feedback, good or bad. Either way, if you want to do thumbs up or thumbs down, or if you want to be more helpful and leave me comments suggesting what's helping and what's not, so that I can make better videos for you, and that way we make sure that the learning is actually solid. So let's understand math behind logistic regression a bit more, and we're sort of trying to get to cross-entropy function here. But we're going to jump around a bit, understand all bits and pieces so that the picture comes together, okay? So imagine you have a fruit predicting robot. You show it a fruit and then it has to guess whether it's an apple, or if it's an orange, okay? So the robot doesn't just say apple or orange. Instead, it gives you sort of this confidence score. It says, hey, like I'm 0.9 or say 90% confident that it's an apple. Or, hey, I'm 0.2 or 20% sure that it's an apple, which means in this case, it is 80% sure that it is an orange, right? Because the choices we have are apple or orange. But sometimes the robot makes mistakes. So we need a way to, say, punish wrong predictions and then reward good ones, okay? So if it makes bad prediction, we say bad robot. And then if it makes good prediction, we're like, okay, good, you're doing good, keep on doing this. And this is what cross-entropy does, okay? So you show a robot an apple and then it says, hey, I am 90% sure that this is an apple. Okay, it gives you 0.95 or 95% sure that it is an apple. 95% is. So that's great. The loss or punishment is very small because the robot made a confident and correct case. So the loss here is just loss here is your log 0.95 negative log 0. Which would be 0.02. That's great. That's a very small loss. And then you show the robot another apple. Let me draw another apple. And then this time it says, hey, I am 0.1 or 10% sure that this is an apple. And that's a bad guess, right? So the punishment should be big because the robot was very, very wrong. So what are we going to do? Our loss is then going to look like negative log 0.10 2.3, which is bigger. It's a big punishment because that was quite a big mistake, right? And then there could be like a third scenario where you give it an apple again, and then it could say like, hey, I'm like 50% sure that it's an apple, 0.5 probability, or 50% sure. Like, it's not completely wrong, but it's not being very confident either. And at this time, I want to give it sort of a medium punishment. I don't want to be too harsh, but at the same time, it does need to know that it made a mistake. So the loss is going to be your negative log 0.50, 0.69. So it's just punishing so that the robot becomes more confident. And what does this mean? Correct or confident predictions, like in this case, have low loss or very small punishment, and then wrong and confident predictions have higher loss, bigger punishment, like this. And then when it has this sort of unsure predictions, then it has medium loss. So cross entropy is like a grading system for our robot. It helps it to be more confident in the right answers, and then it allows it to avoid being confidently wrong, if that makes sense, okay? So we're going to look at the formula now, and we're going to try to understand where the formula comes from. So the cross-entropy formula in logistic regression comes from what's called maximum likelihood estimation and information theory. So let's look at it step by step. So we know that our logistic regression is a probabilistic model, meaning it doesn't just classify a point as 0 or 1, but instead it gives us a probability, right? That's what we looked at. So our probability looks something like this. Y is 1 given x. And then this is derived, or like is equal to what we get from our sigmoid function. What is our sigmoid function? Let me actually write it as this, because that way it'll be clearer, right? Because we feed our z to our sigmoid function, which is e to the power z 1 by 1 plus e to the power negative z. And if you haven't looked at the previous video, this might be confusing. So please do look at the previous video if you're trying to understand the intuition behind sigmoid function. But for now, I'm going to assume that we have our sigmoid function, and then this is where we're getting this value from, our probability from. And what is this z? This z is WTX plus B. And you might say, hey, where did that transpose come from? Why are we doing transpose for that? We've never done that before. I wanted to introduce this because I think it's a good time for us to look at this, and I want to explain where we are getting this transpose from, okay? If that makes sense. Okay, so, and this is a detour. We're going to come back to this, so don't forget this. We're just going on a detour, okay? Detour, understanding this transpose. So, we are predicting apples and oranges, and we're training our model to figure out whether it's an apple as 1 or orange as 0, right? Based on maybe, let's say, our features, our x features could be something like x1 could be like weight, and then x2 could be, what could be a good x2, like a color intensity, say like redness level, right? And weight in terms of gram. So to generalize it, if we have n features for each fruit, then we represent them as a vector, and then okay, our x looks something like this, x1, x2, all the way to your xn. And similarly, we assign each feature a weight, right, our w, and that looks something like this, wn, right? So, and we also have our bias term b, which acts sort of our baseline score for prediction. So when we take the transpose, what happens? Let's understand why the transpose comes. So we need to multiply the weights with the features in order to get our z. That's the goal, right? We want to get our z, a single value, and that means it should look something like this, x2, w2, x2, wn, xn, b, right? That is what it should look like. So in matrix form, this gets written as w transpose x plus b. Why transpose? Because right now, these are both column vectors, and if I want to multiply and get a scalar value, I need at least this. Let me write the b somewhere else. Okay, I need this to be, from a column vector, I need it to be a row vector, so that it looks something like this. Wn, right? So this is a column vector. And this now, the W transpose is a row vector, and their multiplication results in a single number, which is a scalar value. And that's what we're looking for. Our Z, we need a scalar value, which is our raw score for Z. So the transpose, W transpose is needed to properly multiply vectors in matrix notation. That's why it's coming. That's where it's coming from, in case it's confusing. Okay, now let me go back to my notes and then we can continue here. But I hope that detour was helpful, because you're going to see that pop up a lot, and you have to understand why. Because if you're not understanding that, it's going to be difficult to code it at some point. Okay, so we have this, and what does this mean? Going back, if our y is close to 1, that means the model is confident that the input is class 1, so it's confident that it's an apple. If my y hat is close to 0, then the model is confident that the input is class 0, or it's confident that it's an orange, right? Now let's move towards maximum likelihood function. So we want to find the best parameters for our w and b, so that the model assigns high probability to the correct labels. Okay, makes sense? Oh, I am really running out of battery. Okay, I'm going to try to be quick about it. So for each training example, xi, yi, which is your training example, we're predicting a yi, which is the probability of yi equals to 1, right? So if the actual label yi equals to 1, then the probability that the model should assign py equals to 1, given the x, is your y hat. And then if the actual label is, say, 0, then the model should predict py equals to 0 given your x, right? And that is going to look like that. So for each data point, the probability of observing the correct label given the input and parameter is then py equals to yi given xi is going to be your yi to the power yi 1 minus yi 1 minus yi. And if this seems confusing, please check out the last video because we've walked through an example and that has made it very, very easier to understand where this is coming from. Okay, so I'm going to assume that you understand where this is coming from based on our discussion in the last video. So if we look at the entire data set with endpoints, then the likelihood function, which we want to maximize, will look like this, right? We've done this before in the last video, so this is a recap. yi1 minus y hat 1 minus yi. So since multiplying many small probabilities here can cause numerical issues because we're multiplying 0.00 times 0.00 and it just becomes so small that our machine or our computer might not be able to pick up the precision that we want. What we do is take this and do log, and we take log of this function, and this is the log likelihood, and when we take log of this function it looks something like this. Me 1 n yi log yi plus 1 minus yi log 1 minus yi. Okay, makes sense? Okay, and in optimization, it's sort of common to minimize a function rather than maximize it. We're going to talk about gradient descent versus ascent in the next video. So you might be seeing negative sometimes because they're trying to minimize a function, and then sometimes you might just see it as a positive if they're trying to maximize a function. Either way, they're trying to find the optimal point. But this is what cross-entropy loss looks like. This is what it is. And how does the loss work? So it encourages confident prediction. If your yi is 1 and then y hat is then closer to 1, that the term log yi is almost 0, like we looked at the very beginning, meaning there's low loss. And then yi is 1 but hat is 0, then log yi is a large negative number leading to a high loss. But yi is 0, then the second term log 1 minus y hat I ensures some effect. And there is stronger penalization for confident wrong predictions, which forces the model to adjust parameters quickly. And unlike our mean squared error, which leads to vanishing gradients, cross-entropy provides good gradients even for small probability values. Okay, so the cross-entropy formula just comes from the maximum likelihood estimation. It ensures that the model assigns high probabilities to correct labels and low probabilities to incorrect ones, and it's sort of the best choice for binary classification tasks given its nature. Okay, so I hope I helped you understand this. As a bonus, what I'm going to do, I realized, is